I'm back, and it's bonus time. All right, so you can take your pencil, you can put it down, because I just want to show you a couple of things here that it's going to blow your mind. All right, it has nothing to do with the lab. Okay, no, you don't get to fast forward me. All right, so it's going to be really cool. You're going to go ooh and ah when you see this. Really? Okay, let's go up to here. So this was called the what? The how fast equation. And what I'm going to do is I'm going to multiply both sides of the equation by the letter m. So I'm going to put an m here, I'm going to put an m here, and I'm going to put an m there. Okay? Now what, you should know, what is mv? That's momentum, right? So then we could write that this is the final momentum has to equal the initial momentum. Okay, now, do you remember what's ma? Mass times acceleration, Newton's second law. That was equal to force. And then we still got this t over here. See where I'm going? Okay, so now I'm going to take this over to the other side. And so what's that going to be? The change in the momentum is equal to F times t, which is impulse. I want to hear you say it. Ooh, ah. You're still not excited? Okay, let's take a look at this one. So you see this equation right here? So what was that one called? That was the hybrid. What are we going to do? Let's multiply both sides of the equation by m. So we get an m for all of that. Okay, that's an n, an m. And then let's divide both sides of the equation by 2. So that would get rid of this one. And then you'd have a 1/2 right there. And you'd have a 1/2 right there. And so let's take this over to the other side. And what would that be? That would be the change in the kinetic energy. And then that's going to be equal to this side over here. So what was m times a? So that was force. And then force times distance, and that is this equation right there. Did you? You better be oohing and ahhing, because that's good stuff. I mean, that's good physics right there. So that these equations for motion are really trying to tell you conservation of momentum and then conservation of energy. I hope you enjoyed that. All right, so now on to part 3. So we're going to go to the internet and we're going to search for O physics. And then this is what you ought to see. So let me just go to it. All right, now we're going to go to look at all of these different simulations for different things that you can do. So the one that we want is going to be conservation ones. And then we're going to go down to the ballistic pendulum. So that's going to be this one right here. All right, so that's the simulation that we're going to be using for parts 3 and 4. All right, now we're going to, it says to click on fire. And so what that's going to do is it's going to fire a bullet. Okay, so you see here's a bullet that's going to be fired into this block. Okay, now over here it tells you what is the mass of the bullet. Okay, now this has to be in kilograms because the kilogram is the official metric unit for mass. And then this is the block, and it tells you what is the mass of the block. So you can change the mass of the bullet, you can change the mass of the block, and then you can also, so let's go ahead and hit the fire button. Okay, and what did it do? So it's turned that thing into a pendulum, which is why they call it a ballistic pendulum. Now, eventually that thing would come to a stop, but there's no friction on this simulation, so it's just going to keep doing that forever and ever. Okay, now let me go back and then reset it. So I'm going to reset it, and now this thing over here is telling you the height where the center of the block is. So this is the center of the block, and it's at this height right here. Okay, now when you fire it, what you're going to be doing is you're going to take this thing and you see you can raise it and you can lower it. So what you want to do is raise it until it's in line with the block when it's at the top of its swing. So you see the bullet there? So when that bullet is at the top of its swing, then take this line and put it so that it corresponds with it. So I'll let you do that. So it looks like it needs to go up just a tiny bit more. Yeah, right about there. But you do it for yourself, okay? So it's important that you find the initial height of the ball and then the final height of the ball once it's embedded in there. So let's go back to the lab here. Okay, go back to your lab on linear momentum. And then there were two kinds of collisions, the elastic collision and the inelastic collision. So which kind of collision was this? If the ball hits an object and sticks to it, what kind of collision was that? It's very important that you know which one it is. So it's either the elastic or the inelastic collision. Okay, here are the three equations for conservation of linear momentum. Oops, I forgot to put them in there. Okay, you want to do them? All right, so I think we can erase a whole bunch of this stuff now. How's the weather? Are you enjoying this? I hope that you haven't turned me off at this point, that you're still with me. If you're one of my students, you know you can pretty much do these labs without me. But I give you some interesting, I give you stories while I do this, and you know, so this is pretty good. Okay, so we had three equations that we did for when we talked about linear momentum. And so the first one was the one where it was an explosion. And so in that one, we said that you had the mass of particle 1 plus the mass of particle 2, and then it was times the velocity that you began with, so initial velocity, and then it was equal to the momentum of particle 1 times the speed of particle 1, its final one, plus the mass of particle 2, and then the speed of particle 2, and then it was the final one. So this one was called the explosion equation. Okay, then you had the two collision equations. Now I don't want to give it away, okay? It's not going to be this one. So you're not going to use that equation. You're going to use one of these other two that I'm going to give you. So the other one, so the next one, is the opposite of this one. So we're essentially going to take this and then flip it over like that. so that we're going to have the mass of particle 1 times the initial speed of particle 1 plus the mass of particle 2 and then the speed of particle 2 initial, and then that's going to be equal to m1 plus m2 and then the final speed of them put together. So that was another one of the conservation of momentum equations. Then you had another one which said that this was the most complicated, m1 v1 initial plus m2 v2 initial, and then it's going to equal m1 v1 final plus m2 v2 final. So this was another kind of collision. So you're going to use either this equation or you're going to use this equation to find the final speed of the block when it's got the bullet in it. So initially the block's not moving, but the bullet is. So that bullet has momentum. When it hits the block, and then the block now has a new mass, and then it's going to have a certain speed, and that's the reason why the block is going up into the air, is because it's got speed now. So you want to take the mass of the bullet, the mass of the block, the speed of the bullet, and then plug it into one of these two equations, okay, and then solve it for the final speed. So you go ahead and do that for me. And then it says here to record your results in the table below, and then compare your answer to what the velocity slider says. So once you got this done, then if you go back to, you see it's still swinging. So if you go back to this, you can actually read what is the speed. And so you can compare your answer to what the simulation says. So here we've got mass of the bullet, record that here. Initial velocity of the bullet, record that here. Mass of the block, initial velocity of the block, mass of the bullet and the block when they're put together. Okay, final calculated velocity using the equation, and then look at the computer simulation and then write down what is the velocity from the simulation. Okay, got it? All right, so that's part 3, and now we're ready for part 4 in just a moment.